Last topic for chapter 31 is all about transformers. I promise I won't use my joke about more than meets the eye, but there you go, I just used the joke. What exactly is a transformer? The transformer is taking the voltage out of the wall and it's turning it into a different voltage, okay? So this is why you have like a big old power brick for like, think about Nick's computer, like his gaming laptop. There is basically a giant brick attached to it. What that's doing is transforming the voltage out of the wall into something that his laptop can use, okay? I suggest you look at the diagram for the transformer at the end of the chapter. I'm really bad at drawing this, so I recommend you look there. Basically what we're using here is we're going to use Faraday's law of induction to induce a current inside of a secondary wire. So we have a primary wire, then we have a secondary wire. We're going to induce a current in the secondary wire due to the primary wire. The only difference between the two wires is the number of turns of the inductor. So that's what we're going to use to either step up or step down the voltage. So we're going to use Faraday's law here. We know that we're going to have an induced EMF, and that induced EMF per turn is going to be equal to d phi b dt. So we know that we induce a current, we know we induce an EMF based off of the changing magnetic flux. We're not worried about the minus sign right now. Now we're going to have this every time there is a turn of the inductor. So look at the diagram of the picture. Every one of those turns we're going to get an induced EMF. Now thankfully the two EMFs are going to be the same. So the voltages are going to be different, but it's going to be the same EMF for both the primary and the secondary wire. Let me show you. So the voltage in the primary wire, is equal to the EMF per turn multiplied by the number of turns. So this is voltage primary, this is the EMF per turn, forgot an R in there, per turn, and that's the number of turns of the primary wire. We do the same thing for the secondary wire. So the secondary wire is equal to the EMF per turn multiplied by the number of the secondary wire. Now thankfully, both of these EMFs are the same. We use a hunk of metal between the two inductors to make sure that that EMF is going to be the same. If that is true, then what that means is that V primary over N primary is equal to E for the turn. So all I did here was just move the number of turns over into the denominator on this side. And I'm going to do the same thing over here, move the secondary over to the other side. So that's going to be equal to the voltage of the secondary divided by the number of turns of the secondary. So what this means is that the secondary voltage that we create inside of that second wire is going to be equal to the primary multiplied by N secondary over N primary. So this is the big one that you need to know. The voltage in the secondary wire is equal to the voltage in the primary wire multiplied by the number of turns in the secondary divided by the number of turns in the primary. Okay? So that's pretty straightforward. Now by energy conservation, we have to have the same energy in both the primary and the secondary wire. This is where it gets a little hinky. So by energy conservation, we have to have the same power in both the primary and the secondary wire. That means I primary, V primary must be equal to I secondary, V secondary. Okay? But we just got done saying that, let me make sure I do the notation right here. I just want to make sure we're doing the notation right. V primary is going to come over to the other side. So what I'm going to have here is I of the primary is equal to I of the secondary, V of the secondary divided by V of the primary. So I move the primary over. The primary is going to be related to NP over NS. If I solve this the other way, just want to make sure my notes real quick. Just want to make sure my notes. Probably would have been easier to just do VS. But that's neither here nor there. Yeah, so if I just do VS, let's just use VS. So let's use VS right here, so that's going to be V primary, N secondary over N primary. So the V primary is going to cancel out, and that means that the primary current is going to be equal to the secondary current multiplied by N primary over N secondary. Nope. N primary over N. Here we go. Okay. I did it in 2 shots, guys. Okay? So that's what I have right now. I have I of the primary is equal to I of the secondary, NS over NP. And that makes sense here because I replaced VS right here. Now thankfully, I can then get what the current is in the secondary wire. So this is the induced current in the secondary wire is going to be I of the primary multiplied by N primary over NS. These are the 2 relationships that we're looking for. The voltage in the secondary wire is V primary NS over NP, but the current in the secondary is going to be I of the primary NP over NS. So notice that we flip them. It's not NS over NP for the secondary current. It is reversed, okay? It's reversed. Okay, finally we want to take a look at what does the equivalent resistance look like on the secondary wire. So please pause, take a look at this. Now we want to see what does the equivalent resistance look like in the secondary wire, okay? So let's remind ourselves that I of the secondary is equal to V of the secondary divided by the resistance. Okay, so I'm using Ohm's law here right now. V of the secondary is equal to I secondary over the resistance. I'm going to use the fact that I secondary from before is equal to IP NP over NS, okay? So I'm going to use I of the secondary is equal to IP NP over NS. Let me make sure I did that right. Yep, and then I'm going to use that VS is equal to VP NS over MP. So VS is equal to VP NS over VP. So I'm going to use both of these quantities. So IS I'm going to replace right here. VS I'm going to replace right here. Let me make sure I go ahead and do that real quick. Okie dokie. So IS is going to be IP NP over NS. VS is going to be replaced by this, so that's going to be VP NS over NP. And then that's all over the resistance. Okay, that's all over the resistance. Let me make sure I like what's going on there. Okay, so the NP can come over, the NS can come over, and then I can put the R over on the other side. That looks pretty good. Okay, so I'm going to have, all right. So now I'm going to have IP. I'm going to do this in a couple of steps. My notes are a little bad on this. I'm going to do VP, bring the NP over down here into the denominator, NS up here into the numerator. So I'm going to have VP, and this is going to be NS over NP. This whole thing is squared, divided by the resistance. Let me make sure I agree with that. Okay, that looks good. We want to use that IP is equal to VP over R. So I'm using Ohm's law again. Exactly what I started with here, I'm using it again here. So the only difference here is I've got some kind of new R that's floating around down there. Some REQ, an equivalent resistance that the primary circuit sees. So I want to figure out, what does the primary circuit think the actual resistance for this whole thing is? Okay? So right now what that means here is since I've got IP, VP, REQ, the only factor I've got here is an NS over NP, the quantity squared. So I can say that 1 over REQ, that's this guy right here, is equal to 1 over R multiplied by NS over NP, the quantity squared. Okay? So when I solve for that equivalent resistance, the equivalent resistance is going to be equal to, bring REQ over here, bring R over here, and then flip this sucker, and you're going to have NP over NS, the quantity squared, multiplied by the resistance. So this is the equivalent resistance that the AC generator sees, okay? So keep that in mind. Usually with these problems, they're only going to ask you what is the secondary current given number of turns and the primary current, or the voltage secondary given a primary voltage and the number of turns. Don't need to stress too much about this. Again, this chapter has been almost entirely plug and chug.